All right, now the next awesome and amazing thing we can figure out is what is called escape speed, which means what speed would you have to throw an object from the Earth's surface so that it never comes back? Now, you may be able to think of something or someone that you would like this to happen to, but we're going to be nice about it. We're only going to get objects that we're trying to get away from the Earth to escape velocity. Maybe the bad news, even if you escape from Earth, your object that you're trying to get rid of will just start orbiting the sun. So if you're really trying to get rid of something, you're going to have to escape from the solar system, which is a higher speed will be needed. But with just these equations that we got so far, we can figure out how fast you'd have to throw an object so it never comes back to Earth. Okay, what the heck does this mean? So let's do it from the North Pole right here. I'm over here at the North Pole. Why do I want to do that? Because I want to assume that the object's at rest. And if you, relative to the Earth, the object at the North Pole, it is spinning around like this, all the way around. In one day, it'll spin around, completely 360 degrees, but it's essentially at rest. So if you're literally sitting on the North Pole, you've got relatively no kinetic energy compared to the Earth. So how fast do you have to throw this? We call that V escape, so that it will never come back. Now, what the heck does that mean? It never comes back. How much energy does it have to never come back? This is a major conceptual coup if you can figure this out, because it means that you understand how we're dealing with gravitational potential energy. Well, I'll give you a couple hints. How far away does it have to get? It has to get to r equals infinity to be escaped. It has to be able to get there. But it's okay if it gets there and it's got zero speed. We don't mind if it's got zero speed. Once it gets to infinity, it's never coming back. So V equals 0 is fine. So its total energy, its kinetic energy, will be 0 when it gets there. It could have some speed, but we don't need it to have any speed left over. So V equals 0 is okay. V final equals 0 is fine. How much gravitational potential energy will it have? At infinity, that is the only place where the gravitational potential energy of our entire system, of our Earth and escaping mass system, will be 0. So the final energy of this thing, all we need that to be is 0. What do we need the initial energy to be so that it will escape? I'll let you think about that for a second. What do we need its total energy to be when we start it off, when we throw it right there away from the Earth so that it'll get to infinity at 0 speed? Well, using energy conservation, you may be able to guess. Let's take a look at this next step right here. Okay, so E initial, and we do not want to have to do any additional work. We want to give it, in other words, we want to know how fast it's got to already be going so that it'll make it there. So we do not want to do any work on it. We just want to know, like, how fast does it have to be to start with when we throw it. In other words, you throw it at what speed? It's already got the energy. It'll make it all the way to infinity and it'll end up there at 0 speed. So we're trying to find out how much kinetic energy it already has to be able to escape. So our initial energy is going to be kinetic and gravitational potential. They may say, but we're starting on the surface of the Earth. Again, you can't use MGH. For pretty much anything in this chapter, you can't use MGH unless you really know what you're doing, and we'll do an example of that in a second. The kinetic energy and the initial kinetic energy and the initial gravitational potential energy, universal gravitational potential energy, have to add to 0. They've both got to add to 0 so that it can make it to infinity with 0 speed. In other words, if you have a total energy of 0, kinetic energy is positive, gravitational potential energy is negative, that means you've got enough energy to make it to r equals infinity, because there, it's okay if we have 0 speed there, your gravitational potential energy will be 0, so your total energy will be 0 when you're all done as well. So as long as your initial energy, and we have to use universal gravitational energy, is 0, you'll make it there. So let's go ahead and just rewrite this. 1/2 mv squared. You might ask yourself, well, JB did all that derivation. Why isn't he using that other equation for kinetic energy? This is not a satellite in orbit. This is something that we're throwing at high speed away from the Earth. It's not going to be in orbit. We must use 1/2 mv squared. You can't use GMM over 2r. It won't be. It's not in orbit. You must use this. So that's its kinetic energy initial. Its gravitational potential energy initial is this. Notice it's on the surface of the Earth. So this is why it's G, mass of the Earth, times the mass of our object we're throwing, over the radius of the Earth. We can neglect the radius of our object because it's so small. That has to add up to 0, meaning it's got to be able to make it infinitely far away, and it's okay if it's at rest there. But if these two things add up to 0, then we are at the right speed for this thing to get the heck out of here and never come back. So all I'm doing here is just deriving the equation for speed. Let's go ahead and finish that up. And what we get is that, notice that the mass can cancel from both sides. I just added this to both sides. Mass cancels right there. Get rid of mass, get rid of mass. And then I've got multiply both sides by 2, and that's what I end up with right here. So v squared is equal to 2 gm, mass of the Earth, over the radius of the Earth, and I just take the square root of both sides. So all we do is we solve for v right there, and you will find that when you do this for Earth, notice it doesn't depend on the mass of the object. It does depend on the mass of the Earth and the radius of the Earth, but to get anything the heck out of here so it never comes back, all you need to do is throw it at 11,190 meters per second. This does assume no friction, but if you throw it that fast, it ain't never coming back. It is going to make it how far? To infinity. And when it gets there, how much kinetic energy will it have? Well, when it finally gets there, it will have 0 energy, 0 kinetic energy, but it's so far away that it will never come back. That is it. That is escape velocity.